the microphone picks it up nicely, right?
What are you trying
Like
to
last
do?
time was okay, right?
Okay,
Action.
it is.
Stick my head into
We're
the
on.
ceiling.
We're on.
We are on.
It's buffering.
So I don't think anybody else is coming. Right?
Yeah,
Ankit will
he's
not
gonna
come.
come in about 12, so
Yeah.
I can take it.
So this time you're taking a step back and doing point of view theory again from a new point of view, which is canonical quantization. Before starting that, let's clear up some philosophy. So if you want to write down a relativistic theory for quantum mechanics, the first difficulty is that in quantum mechanics, position is treated as an operator while time is not. So we can do either one of two things. You can promote time to be an operator or demode position to be a label or parameter like time. That's what we do in quantum field theory. So yeah, so we demode x to be just a label. It's not an operator anymore. So in quantum field theory, the operators are the fields, and the fields have a label of x, just like in classical mechanics you have position, and the position has a parameter t. Now the parameter itself is x, where x is time and the spatial part of it. Now one
Only phi is the field.
Yeah.
What is that Q? What's the name?
q,
Yeah.
q is the coordinate. In classical mechanics we have generalized coordinate, that's the name. And this is classical mechanics. This is QFT. This is quantum mechanics. Right. Now, once we have the fields, in quantum mechanics, the way we quantize quantum particle is take the field, take the coordinate, and it's canonically conjugate momentum and impose commutation relations. So we are going to do exactly the same here. So once we have a field, this is our generalized coordinate, and we need the canonically conjugate momentum for this. How do we get the canonically conjugate momentum for a coordinate? Right. What's the definition of speed?
Del Q dot.
Del H over del.
That's P dot.
Del L by del Q.
Oh.
Right. It's dl by dq dot. So to do the same here, we need the Lagrangian. But we know the Lagrangian, we've been using that for a while now. It's this. We're specializing to a real scalar field, so this phi is just a scalar. Now, this can be rewritten as how do we find the canonically conjugate momentum? It's the same definition. So phi has to be denoted, defined to be the d phi dot, which is nothing but phi. It's simple to see from this. This is the only thing that depends on phi. Now the next thing is to impose a commutation relation between phi and phi. Just like in quantum mechanics, we had Q, P, and M is I. This is Q A and this is QB. Now, before doing that, let's do a little bit more work using this guy. So if we have this Lagrangian, how do we find the equations of motion? Use the Euler-Lagrange equations, right? So I leave it as an exercise for you to figure out that the equations of motion corresponding to this is applying Gordon's equation. it, it's worth it. So now let's try to solve this equation. How do we come up with this?
Green's functions.
Very good. Is there a simpler way to solve?
It's a wave equation.
It's a wave equation. So the solutions are plane waves. So usually when you see a differential equation of this kind, what do? You guess phi to be e to the something, plug it back in, solve the algebraic equation, blah blah blah. You make the answer. Exactly. So you make the answer. I don't know how to spell answer. Is that right?
Yes.
Phi goes like e to the plus minus ikx. Let's plug this back into this. So what do we get?
K squared.
Right, so d mu acting on e to the plus minus I kx, where kx is k mu and mu.
So we get plus or minus I K mu E plus or minus I K.
Right? Now, if I take one more d mu from on this, I'll just get another plus or minus I k superscript mu e to the I k blah blah blah. So box will give me minus k squared. And this minus and the new minus will cancel each other and we get this. Right? Now, these are never zero. So in order for this to satisfy this equation, you need k squared equals minus x squared. This is the famous Einstein relation that we have if you rewrite it in a meter way. K squared is nothing but k naught squared plus k vector squared as equals minus n squared. So you get k naught squared is k vector squared plus n squared, which is the familiar form of Einstein's relations. K naught is identified as the energy. Now, once we have these solutions, we can write a general solution for phi. Right, that's standard from the theory of differential equations. Once you have the linear independent solutions, the general solution for phi is a linear combination of these solutions. Right? So how do I write it? So I'm writing an integral because k is a continuous variable. Now what? Integral over what?
K.
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 It's a 4-dimensional k, right? So you said the d4k?
Yeah, D4.
D4K.
It's not a d4k. Why?
D0 is restricted.
Yeah, because k0 is restricted. So I just have to vary k vector. If I vary k vector, I get all k4s possible, k mu's possible, because k naught is determined by k vector itself,
Okay. That makes sense.
right?
Yeah, alright.
So it's d3k, and I'm going to put the factor from say here for convenience, which will determine SU, and then a linear combinations, right? So one solution times a coefficient plus the other solution times a coefficient. So it's a of k. Should this k depend on the 4 vector k or just the vector k?
Just a vector K.
Just the vector k, because the 4 vector dependence is redundant because k naught is known. So I'm going to put an arrow. Now, this A and B relation related in some fashion.
Yes.
What's the relation and why?
Reality condition.
Right, we have, oops, 5 equals 5 star, right? If I take a star as this guy flips signs, and then A star and B star. So we must have B equals A star. So this is the same as B star. Now let's try to find f of k. So the restriction of f of k is that I need this measure to be Lorentz invariant, because we are aiming at the Lorentz invariant theory. The Lagrangian being Lorentz invariant means that the theory will end up being Lorentz invariant. So why not start with the Lorentz invariant measure? D3k is not Lorentz invariant. Why? Is that obvious, or we go through that? So is D3x Lorentz invariant? Why not?
Volume changes.
That's right, that's the thing.
Volume changes. For example, if I have a cube, I start moving along this direction, length contraction and blah blah blah. Same thing for D3k. Right? What is k? K is P is h bar k, and k is 1 over lambda, right?
Mhm.
The de Broglie relations. K is proportional to 1 over lambda. Not de Broglie, de Broglie relations. And when you change to a moving frame, lambda shrinks, and then, oops, what do I miss here?
I think that's right.
Magnitude is what is lambda.
Why was that? And why?
I didn't want to
For
confuse
vector.
with the 4 vector.
Okay, yeah.
So, yeah, for that reason, D3k is also not Lorentz invariant. Now, what is a Lorentz invariant?
Contraction, I guess. KU.
What would be a Lorentz invariant
Measure.
measure? In terms of x or in terms of k, whichever you think is intuitive.
Yeah.
D4k. So let's step back. Why is D4x? This is not Lorentz invariant. Yes, Lorentz invariant.
I guess
Why is that?
D4x is just what? The invariant interval?
No, why is this Lorentz invariant?
Time dilation.
So the
Length
cube
contraction.
gets a Lorentz contraction, but the
Time
sine
dilation.
gets a equivalent time dilation.
Time dilation. So if length contracts by a factor of gamma, time dilates by a factor of gamma, so they go.
Am I not, no, is it somehow related to ds squared? Or is that stupid?
The ds squared?
Yeah.
I don't think it's related to ds squared. No, it's not. ds squared is a line element along the word line. This is just a volume element.
So d4x is d3x dt.
And dt is
That's
a time
fine.
interval.
You're right, so when you d3x prime dt prime,
Yeah.
gammas cancel.
So
Am I-
likewise,
Right?
yeah, that's right. So likewise, D4k is Lorentz invariant. Same effect. If this guy shrinks, then energy gets elongated or something like that. So, but this is not what I want. I want to sum over 3 momentum. I want to get rid of the dk0 term by imposing k naught squared equals. Now, how do I impose such a constraint in an integral? Delta functions. What delta function should I put in?
K0 squared minus K vector squared
Right.
minus n squared.
Right. Or in other words, I can just put it this way. can just demand that k squared must be minus m squared. Right? And what kind of Lorentz transformations am I looking? I'm looking at something called an orthochronous Lorentz transformations, which means that it doesn't flip the sign of time.
Can you repeat the word?
Orthochronous. I looked it up. This means that, if we are doing a Lorentz transformation, right? The picture looks like this, right? This is event number 1, this is event number 2. And if you do a Lorentz transformation, if they are causally connected events, the Lorentz transformation will take this along this lines. Because Lorentz transformations has to preserve this relation, right? And this is a hyperbola, right? Yeah. So, but that's not it. You have this part as well. I don't want a Lorentz transformation that takes me from here to here. That's a discontinuous Lorentz transformation. I cannot achieve it by moving from one frame to another moving frame. It's like rotation, mirror flipping in the case of SOP. Is that clear?
No.
No.
So in the case of rotations, right, or in the case of the group O3, the transformations are orthogonal transformations on a vector, 3-dimensional vector. Maybe take a vector, rotate it. That's part of this group. Also, take that vector and flip it. That's also flip, meaning show that in the mirror. That's also part of this group. But this flipping cannot be achieved by a continuous rotation.
It can do.
Yeah, you can just do this.
No, in 3D.
It's still this.
No, I mean flip, meaning x, y, z to minus x minus y minus z.
Can you give an example of continuous? Like an operation that is continuous.
Rotations. You start from nothing, and infinitesimally go to.
Yeah.
Now you don't get X, Y, Z minus.
Yeah.
So it's going from this to left-handed system.
Or without any points in between, you have to go from minus xyz to xyz.
It's impossible to achieve from rotations. Let's take.
You try to draw them.
Yeah.
Maybe it's easy. It's easy if you try to draw them, and then you convince yourself. One of the axes will always point in the wrong direction if you want to do like flip all 3 signs at the same time.
Let me try to draw something.
The axis of rotation are always fixed. It should be x, y, or z. Is that the case?
Hmm?
I mean, if we are free to choose any axis of rotation, then that is possible.
Yeah, you have to fix the axis of rotation. You shouldn't go from a right-handed coordinate system to a left-handed coordinate system.
I don't see that.
Okay. I think we can do step by step. Like draw an arrow here and consider like x, y, and z, and then flip x, then try to flip y, and then you see the z is not flipped. You understand?
You want to do it?
Yeah,
I can try to. I think I did this once in my life, maybe.
So you can get minus x minus y by rotation.
Yeah.
Minus x minus y plus z. That is achievable by rotation.
I don't have any other color.
Well, this color.
So the point is
Yeah, that's fine. Don't.
That is good.
here. this position on. I don't know, this, some vector. Okay, now I wanna make, which one do I wanna rotate first? Maybe I wanna flip y first. So A has components A, X, A, Y, and Z, right? I wanna flip this one first by a continuous rotation. So if I flip this, I'll get the new axis will be and then I'm terrible at drawing, but Z will still stick out of the paper, right?
Yeah.
Now, whatever component I had in the y-axis, now I have minus that, right? Because
Wait,
y
that's
is flip
not-
y.
Sorry.
I'm following.
So you're rotating the coordinate.
Yeah. Oh, and also I flipped the z component as well, right? Automatically.
No,
But I didn't
you
put-
just rotated along x.
Hmm?
You just rotated along.
I rotated around z, right? Whoop, by 180 degrees. That made this component here a, y, and this component, let me draw it like this.
You rotated along x by 180 degrees. That's how I see it.
That's right.
Yeah, exactly.
Uh-huh.
By 180 degrees. So this will be a original way AY, and this will be the original AZ, right? They were both positive in the first case. I rotated the axis. Now, let me prolongate those things. And again, I can do the same decomposition here. I'm terrible at drawing, but this is my new AZ, new AI. This new AZ is nothing but the negative of the previous one because I didn't change the arrow, just flip the axis. But now z-axis is pointing down instead of up. My new AY is minus the previous AY. Same reason, now y points in this direction. But my AX here was positive. My new AX is still AX. So if by rotating, we could change two of those signs, but the other one to change the other sign, I'll have to flip this x-axis, which is a non-continuous transformation. Just flipping one of them.
Oh, so
That's
you
what
need to-
Ravi was saying, like, we went from,
Left-handed to right-handed to left.
yeah, like that was the case initially, X, Y, and Z. And then if we flip to get all minus signs, flip X here. Which one I use? X, Y,
It is
and
easy
Z,
to
right?
see if you rotate z-axis, along z-axis, right?
Hmm?
It is easy to see in this diagram if you rotate along z-axis, right?
Yeah, I can do this, but then for me it will be harder to draw, I think. Because Z and Y
See the point.
are in the
I
plane.
think you can prove it
But
by.
Just do it, so is mine.
Does that make sense to what I'm trying to say? Like,
Yeah.
remember, my thumb is in the direction of X, my pointing finger is in the direction of Y, and my middle finger is in the direction of Z, right? And I'm using my right hand rule here. If I flip this axis to get all minus sign, now I can only achieve that if I use my left hand rule. My thumb points in the new direction of X. Oh, this one, yeah, this one. This pointing finger should be pointing in the direction of Y, and the middle finger in the direction of Z. And I cannot do the same thing with the right hand. Only
Yeah.
left.
Yeah, you can just try this, take your right hand and left hand, try to.
Yeah,
get
rotate
this
one of them and see if you can
impossible.
align with the other.
No, just like this.
But so I can
Yeah.
only use one rotation. I
You
can't.
can use any number of rotations.
See,
You never.
every time you
What I was
rotate,
thinking
you are
was
switching two
instead of-
signs.
Yeah.
What I was thinking was instead of rotating the coordinate axis, you could do this with a.
It should be the same, right?
It should,
Rotating
but
the,
apparently
the
it should be the same.
yeah.
In 4 dimensions, it should be possible.
It should be
And
possible.
in 2
Yeah.
even
I mean,
dimensions
if I
it
force
should be
myself to think that those axes are in the same place, then I rotate it A.
Yeah.
So what was the?
So the idea is the same here. So I want a Lorentz transformation that doesn't fit the ordering of time. I don't want it to go from this branch to that branch. That's a discontinuous transformation. You can see that it's discontinuous because the curves are discontinuous. So I want to impose that over here. The way I impose it is to introduce a heavy side step.
It's a K raised to J.
It's theta k now.
K what?
K0. So K0 has to be positive and restricting it to the upper branch. Now, how do I convert this to D3K now? It's already D3K. How do I rewrite it in a nice fashion? We use the delta function rule. Delta function of a function x minus x naught by constant value C assignment number something Yagi. So
I'll make it mode 1, 2.
delta.
Yeah, it's right. So measure.
So this is nothing but delta of k naught being equal to square root of k square percent square by if I take a derivative of this guy with respect to k naught, I get a 2.
Maybe.
Yeah.
You shouldn't that be a K? K minus.
So I skip the step. I just want to get rid of the k naught into. So I'm writing in terms of k naught, which now becomes divided by the derivative of this function evaluated at the root, which is square root of k square plus m squared. So derivative is just 2 times k naught evaluated at the root is 2 square root of k vector square plus m squared. That's not all. We have one more contribution from the other root, which is minus of this, which is delta plus square root of square plus m squared by 2 square root. Is that clear?
Yes.
So we don't have to think about this guy because we are restricting k naught to be positive. So if this delta function demands k naught is negative of square root of k square plus m squared, which is something that we don't want. So we can put the first term only over here. So we have d3k dk naught delta k naught minus, let me call this guy as omega subscript k. I put that here. Omega t by, that's it. Right. I've taken care of the theta by dropping this. Is that alright? Or was it too fast? I'm intentionally going too fast. Stop me if you.
It's alright.
So, is that's the case, we can integrate K naught just by dropping the delta functions. I can drop this one and that one. So I get the three-dimensional Lorentzian gradient measure. So I choose f of k to be 2 pi cube 2 omega k. 2 pi cube is conventional and 2 omega k is this guy. So I have it. So once we have that, and to simplify things a bit, to avoid writing, I'm going to not it's going to be noted by dk tilde, just to shorten my writing. Now, alright. Now let's find the canonical moment. So we have the field to be tilde. What was the canonical momentum? It's phi dot. It can be easily found from this, right? What is phi dot? These guys don't have time dependence. Time dependence only sits on the exponentials. And the first exponential has a minus pi k naught k naught t. If you take a derivative of that with respect to t, you get minus I k naught, and that k naught is supposed to be omega k. So I get I omega k, let's say minus I omega k from this guy. From this guy I get a plus I omega k, because it's minus ikx, and kx is nothing but k naught x naught plus k dot x, which is minus omega k t plus. That's this definition. So I get a minus sign over here. Is that alright? Or is it way too fast? It's alright, right? Now we quantize the theory by imposing canonical commutation relations. So if you remember, we had QA at P at B. This was in quantum mechanics. We do the same thing here by imposing a commutation relation between the coordinate, which is the field, and the canonically conjugate momentum. And remember, this was dl by d phi dot, which is how we find the canonical conjugate momentum. So what do we do here? We need to impose phi hat x with phi hat y equals what? There has to be an I, because same thing. What else?
Yeah.
Delta of x minus
Delta of x minus 1, right? What delta?
delta q.
He says 4, she says 4, 3. Which one is correct?
It should be 4.
What?
And why are four-dimensional space-time points?
But it's actually a 3. That's because Heisenberg is happy if you measure position and momentum at different times.
Why do you care about Heisenberg?
Because this is ultimately the Heisenberg's principle, right? You cannot measure the position and the canonically conjugate variable at the same time. So I need to impose this condition that I am looking at this commutator when x naught is equal to y naught. So this is an equal time commutation relation. Then you just have actually 3 variables inside this, each of them. So it's delta 3 x minus 1. And the other commutation relations are trivial. Phi hat of x, phi hat of y, x naught equals y naught is 0, and same for phi. Is this that clear?
Can you run by again why the whole Heisenberg stuff?
So Heisenberg principle states that you cannot measure position and momentum of a particle at the same time.
Yeah.
So in this case, our dynamical variable is the field, and the canonically conjugate momentum is phi.
Sure. Yeah.
So you just have to impose that you cannot measure them at the same time.
Yeah, Dima.
What?
The first line equation in quantum mechanics also depends on time, right?
Yeah.
But this commutation relation
This
is
is
only
not-
valid when both times are the same.
I agree.
Yeah.
Yeah. It's kind of it's
So
immediately.
the extension of it.
It's not immediately obvious that that's the case, but that's absolutely.
You set P and P to
be the same.
Is that a frame independent?
No, that's the thing. We fixed the time
Right.
in some way, right? So this sort of breaks Lorentz invariance. But you can do a lot of hard work to show that in the end everything works out to be Lorentz covariant, which I will not do, which is what I assigned as a reading last week. But it's okay. All right. Now, this is also part of the reading. Once you have this, you can use this and this together to show that the predicate relations for A and A dagger, A prime is any guesses? I mean, some hand wavy guesses. There has to be delta cube of K minus K prime.
Well, I mean, I understand that these are, never mind. So I remember, I know that we eventually interpret A as an operator.
Yeah.
But did we mention that any time before?
Yeah. I made these into hats, right?
Oh,
So these have hats now, and I changed star to dagger to fancify things. So these are hats. This happens after this. Once we have this, then you can derive the following, which is the statement I made. There has to be delta 3 of K minus K prime. Right? And I don't think it's obvious, but the result turns out to be 2 by 2, be okay. Delta 3 in so this is a homework. I don't want to derive it, man. It's just a waste of time. Alright, now the next task is to find the spectrum of the theory. How do we find the spectrum of the theory? What operator do we use?
Like it, take it from the. So what we're gonna wanna do is operate with the Hamiltonian,
Right, so we need to find the
the
Hamiltonian.
Lagrangian. So
So we need to find the Hamiltonian. So how do we find the Hamiltonian?
What we're going to do is PQ minus L. Yes.
Correct.
Minus that.
Now say that in terms of fields. That was right. So
Legendre transformation?
the general transformation.
That is it?
Yeah.
Well,
What
right.
he gets the dynamic.
That's pretty
So
advanced.
can you tell me what?
Minus L.
Phi dot
Minus L. Before that, something is there.
phi not
Phi dot. Right, it's the classic thing. It's PQ dot minus L. P here is phi, oops, and Q here is phi. So the dynamical variable is phi, blah 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 blah.
phi square.
So you can derive this, which is also part of the homework, and get this, which is also sort of easy to get. So, 25 and this is easy to see as well, right? Because we had the Lagrangian to be half phi dot square and half the 5 squared and half n squared, 5 squared. So you can think of this as the kinetic energy term and this as the potential energy. So the Hamiltonian is kinetic energy plus the potential energy, but you replace phi dot with pi. That's all we have done. So this is something you think about. Now I'm going to do something for good luck. I'm going to add a constant to the Hamiltonian. It's just a constant. I can always add a constant to the Lagrangian, right? Doesn't do anything. You've learned, because if you had a total time derivative of something, doesn't change anything. But it will turn out to be useful, and this is going to be our first glimpse at counter terms and renormalization. So now this is the Hamiltonian density. How do you find the Hamiltonian? Integrate over what?
D4x.
time
Two answers.
One minus
Both
the
are
other.
wrong.
One minus the other.
d dot
It's d4x divided by dt. It's d3x. It's the Hamiltonian density, right? So how do you go from density to, you know, mass integrated over the volume? d3x x. Now comes the task of finding this Hamiltonian in terms of A and A dagger. Should I assign it as homework or should I do it? What do you think?
Do you have the
No.
notes with you? Like,
Do it for homework.
are you gonna skip some steps? Or is-
I'll skip a lot of steps. Yeah.
okay, that will be long if you try to do it
Yeah.
yourself now.
So let's do it quickly. So I have a look at this. So from this guy, oops, I'll just get minus omega naught times the volume of the space, which is infinite if you think about it. Then you have integral d3x dk tilde. So I'm going to plug these guys in, and these guys comes in squares, phi dot squares, pi squares, and phi squares. So if you have squares of these kind of things, you will have two integration variables, d tilde k and d tilde k prime, because that's how you square an integral, right? So integral dx f of x squared is integral dx dy f of fy. So then all of these terms have a half, which I'm gonna take out. F. Alright, it's too much writing now. Oh. Yeah, let me do this here. Minus I omega. I'm dropping the subscript k because I don't want to write it. A E I A x plus I omega A dash E minus I A x. That's 1 pi. Now you have to multiply it by another pi which has a k prime. So minus I omega prime A prime to the I A prime x. I omega prime A prime dagger to the minus I A prime x. You see the point, right? It's going to be very long. That's just the first term, pi square by 2. You have similar terms here. This algebra you have to do yourself at least once in your lifetime. I've done it several times. I did it yesterday
Pi
also.
square by 2 isn't it just like 5?
So let
Hmm?
me
Pi square you can approximate as 10.
quite a lot of steps.
What if that's 7?
Let's quickly see what this could be. So when you multiply this thing out, you have two kinds of terms. One, e to the plus something multiplying e to the plus something, and the cross terms, right? Yeah. For the cross terms, you can integrate out d3x and get a delta function, and delta function of k minus k prime. And using one of the d3k prime integrals, you can get rid of the delta functions. So for the cross terms, k will be equal to k prime. For the non-cross terms, k will be equal to minus k prime. Because this guy will become e to the I k plus k prime x. And when you integrate it out, you have a delta function of k plus k prime.
What do you mean by the cross term and non-cross term?
This is a cross term. With the plus and the minus, I call it a cross term. So just word it.
That's delta k,
Delta 3k.
right, but only when you integrate over
X.
d3x.
Yeah. And once we have a delta, you can integrate over d3k prime and do it yourself. So, right, you end up with this. So you see how we get rid of two of the integrals, right? In the end, we have one dk integral left over. They don't care about this something because this is 0. So this is 0. So I end up with
Did you
this.
drop the subscript and term?
Did I stop? Yeah, I dropped something. So I thought that was strategy. So omega k square plus m square is again omega k squared, right? Where was it? Did I erase it? Yes, so omega k squared plus k squared plus m squared. That's how we defined it. So I can just put this guy out and have a 2 here. And I can get rid of this 2. I can get rid of this guy and this 2. Right?
How did you get a 2 omega in the denominator?
Because D3K prime comes with the,
Oh yeah, okay, that
2 omega.
should.
I think we like a lot of that stuff.
What?
We see a lot of vomit influence.
Yeah. I get influenced by all the good teachers.
Like you keep that. We're still recording.
Yes.
So this is what we end up. Now, if we use this, right? I want to rewrite this in terms of, just A dagger times A. Yeah, not, so we're gonna use that. So, if you remember harmonic oscillators, the Hamiltonian is written as A dagger A, right? That's called a normal ordering because, if you have A dagger A, if you hit it on 0 from the right, you get 0. If you hit it from the 0 on the left, you still get 0. So it's always a good idea to order A's and A daggers such that all the A daggers comes to the left, all the A's goes to the right.
If you hit it from the right, you get absolute zero like none. But if you hit it from the right, you get state zero. Isn't that true?
No.
The A dagger would raise it to. Oh, it's okay. Sorry. Yeah.
A on 0 is 0,
Right.
if you flip that, you
It
get
becomes zero.
Should the A's have the hat?
yes, A should have that. It's too much right now.
Yeah, just wanted to make sure.
So, what was I saying? Yeah, it's always a good idea to order A's and A daggers in such a way that A daggers comes to the left, A's goes to the right, which is incidentally called the normal order. So I want to do the same here. So the way to do it is to use this graph. So if you notice here that both A and A dagger has the same momentum label. If I use the same momentum label here, I get a delta 3 of 0. So using this, I can say that A dagger K is equal to A dagger K plus 2 pi q to omega K delta 3 is 0. That's clear, right? I'm just using it for K equals K prime. So that gives me this. So if I change this term for this term, I get twice A dagger K AK, and that 2 goes with this 2. So I have omega K, A dagger K, K, and the other term, which is this integral. So, right. Integral E K tilde 2 pi q omega squared K. So omega squared comes because you have an omega here and an omega there. Both together gives me an omega squared. So if I use the definition of D3K as, not D3K, D2K as, I can cancel out these guys, I can cancel out these guys, and we put the 2 over what about this term? Is it finite or infinite? It's obviously infinite because you have a delta 3 of 0. So it's actually twofold. That's the tricky part here. So let's look at delta 3 of 0 first.
What do you mean by twofold?
I will explain. So let's look at the first infinity, delta 3 of 0. What is the definition of a momentum delta function? Integral
TQP
dx
e to the power
e to the power
IK
plus or minus, I don't remember, ik dot x, right?
by root 2.
But you have to set k to 0. So that is just integral d3x, which is the body. Is that alright? So, one of the infinities is coming because space is infinitely large. So we remedy that issue by, thinking about measuring energy located in a localized region by measuring energy densities rather than the energy of the entire space, which doesn't make sense. Like, how do you measure the energy of everything? It's impossible. You can only do an experiment here, which I don't know how to measure energy at all. So there's no point talking. So I'm going to get rid of this term, common influence, and put a V, because delta 3 is this. Now I still have this. After getting rid of the delta, I have this. Is this finite or infinite?
Yeah, but isn't it infinite?
It is infinite. Why?
A and Z infinite.
Yeah, but what about this guy?
K square
What
same
is K
square.
squared plus?
It's k square plus m square, right? So let's estimate this guy for. Let's put an upper limit lambda and let lambda go to infinity. Then d3k is nothing but 4 pi k squared dk using spherical coordinates, and omega k is square root of k squared plus m squared by 2. And for very large k, I can drop this m squared. So this just becomes k by 2. So this goes like some factors of pi 2 blah 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 k cubed dk, which is lambda to the 4. If you remember Bauman doing something like this in class for the vacuum energy. So if you look at this, you can see that this is sort of summing up omega k by 2 for every point in momentum space. So this is sort of where we can see why she was talking about harmonic oscillators at every point in momentum space. Omega k by 2 is the ground state energy for a harmonic oscillator. And if we have one harmonic oscillator per every point in momentum space, you're bound to get infinite energy. So what do I do next? Let me call this guy epsilon naught. This is the energy density of an infinite number of harmonic oscillators. Why is it an energy density? Because I took out the volume factor already. Or another way to see that is to look at the dimensions. This has the dimensions of energy, and d3k has the dimensions of 1 over volume. Right? So overall, combined this term and the epsilon naught times b. So what should I choose omega naught to be?
So that, what's our aim?
This is infinite.
Yeah.
I don't want it.
Just,
And that's
can you
good.
say omega 0 equals to epsilon 0?
Yeah. So we renormalized theory by choosing this. So we added a counter term in the Lagrangian such that it cancels an infinity.
So omega naught is arbitrary, how did you set it to epsilon naught? Is it just,
It's arbitrary.
that's how you define it? So you're adding a potential so that any
It's
time.
not a potential.
What's,
It's just a constant.
no, but it's a coefficient of potential, right?
No.
It's just a constant.
That omega naught v, why do you
It's
say?
just a constant.
V
V is
is
the
not a
volume.
potential.
V comes because of this V3x of h. And h had a minus omega naught. If I take a volume integral, I get a volume factor. V is not a potential.
Oh, you added omega naught, yeah, I remember you
Yeah.
did that, yeah.
Just that is just for good luck.
So that, that good luck was to get rid of epsilon
Yeah.
naught. That's, this whole process is renormalization?
Right.
Where you,
This is a trivial example of renormalization.
where you add something arbitrary so that you can.
You add an infinity to the Lagrangian to cancel an infinity that you get later.
So there's an infinity in the free field?
Yes, so in that sense, the Lagrangian is infinite. How do you interpret renormalization? I have no clue.
It's like a gimmick, right?
Yeah,
Then
you can think of it as a math trick maybe. How do you think of it, man? I don't know.
And in this sense, the only thing I can say is that like we can measure only differences in energy if you're not talking about gravity, so it's irrelevant to sum a constant or subtract a constant in the Hamiltonian, right? Hamiltonian is energy. We're just shifting
The Hamilton.
what is zero of
Yeah,
energy.
but shifting by an infinite number of.
Yeah, but still, that's the
It's
best
just
we
shift.
can do in trying to intuitively explain that shit.
But, you know, try to grapple with this idea because you're going to see it a lot. In a
This
more-
is a easy to explain example of normalization.
Yeah.
The other ones are terrible, I think.
So just to be clear, you know, there will be, when we do 5-4 theory,
Mhm.
there'll be something we ought to count
Yeah,
terms.
so, for example, the propagator, the mass of the phi particle will turn out to be infinite. So what you do is write the mass of the phi 4 particle to be a finite term plus infinity. This is infinite. This will turn out to be, let's say. I'm not sure if I'm writing it correctly, but yeah.
It doesn't
There's the
matter, right?
bare
Doesn't
mass.
matter. So the physical mass you have to measure it from the experiment.
Yeah.
Then you set
Hmm.
this m to be the physical mass. But I started off with a different Lagrangian, right? This was a different term. So where's the additional piece? That's the counter term. We'll get there.
Yeah, normally, right, when you renormalize, you have to include some parameter that's only measurable from experiment.
Yeah.
So right now, we've just said omega naught equals epsilon naught, but we haven't,
So the vacuum energy has to be measured. The dark energy, if you wish.
What kind of
But what-
bothers me in field theory is more when you renormalize the coupling constant. Because it seems to me we're first expanding on parameter that we assume to be small, but it's actually infinite.
Yeah.
And then with something else to the Lagrangian such that this parameter agrees with the experiment. And then if this experimental parameter is smaller than one, in dimensionless parameter is smaller than one, then okay, we justify our initial expansion. Even though we were expanding around infinite parameter. At least from my point of view, that's so confusing. I don't understand. I don't quite understand how to justify the Taylor expansions they do. perturbation theory.
That's
I
basically.
think we should, David, do you have a take on that?
No.
Should we interpret that we are from the start expanding around not the bare
Yeah, that's
coupling,
probably
but-
the take.
That's
I
what,
don't see that.
is that what we did in PQ's class? Where he expanded some insane thing. And then he said, look at all this crazy, all these terms. It's basically an infinite expansion.
Yeah,
That is what we saw in PQ's class, right?
yeah, we saw that, but the issue is, for this expansion to be sensible, in the sense of, if you wanna truncate the expansion, then the parameter has to be smaller than 1, right?
Yeah,
Because it's like, lambda will be greater than lambda squared, which
Yeah,
will be
yeah.
greater than lambda cube, which will be greater than lambda fourth. But if lambda is in infinity, it's like way bigger than
Yeah.
1. So every term in the expansion, in the Taylor series, should actually contribute more and more.
Yeah.
But instead we say, let's forget about it. I mean,
Maybe,
a priori it's
maybe
infinity.
Professor
infinity.
Abdul Makul will.
That's right.
A priori it's infinity.
Is
But,
that understand?
hmm?
Is he
So, so let me explain one more thing. So,
Oh,
we have the
that's-
Hamiltonian now.
QFT.
Yeah, yeah,
We have the Hamilton.
That's what he's understand.
What's the difference between physical mass,
Maybe.
bare mass,
Yes, but
and
it's
just
not
mass?
Physical mass is a
I
physical
do not
mass.
Can you measure it?
Bare mass is a parameter in the Lagrangian. That's all.
And I remember, PQ said
That's
bare mass is infinite.
Yeah.
What is it?
That's the
It has
person mass.
Brazilian
And
political
not- and
is a joke
Yeah, and not as
regarding
the
Brazilian politics.
bare
It's
mass.
hard to, it's
How
hard.
do you relate it?
We'll get there. That's my answer. So we get rid of this term by setting this condition. So we have the Hamiltonian to be just this. So now let's look at the spectrum of H. So E is an energy eigenstate of H. Then you can show that A dagger A E is also eigenstate of H is energy, and you guess the energy of this state. E is an eigenstate, A dagger is also an eigenstate, which is Homer. Can you guess the energy? Right, it's E plus W, just the harmonic oscillation. So if I have AK instead of A dagger T, what would be the energy? Minus, right? And the Hamiltonian is positive definite, meaning it cannot have eigenvalues less than 0. Why is that? To prove that, it's easy, very easy to prove. If I take this guy and hit it with E on both sides, I get right? And H goes like A dagger A, right? So I'm just going to sketch it. So since H goes like A dagger A, this is E. It's an integral and all that stuff. But it just goes like A dagger A. Like this.
Yeah, I'm sorry, I got hung up on.
If I define AE as psi, then I just have psi you see. So the norm of any vector has to be greater than or equal to 1, equal to 0. So this means that this is true. So if A lowers the energy and E cannot be smaller than 0, then there has to be a ground state. Is that statement true? So there exists 0 such that AK and 0 is 0. Oops, 0. Now what's the energy of the ground state? What is H at T1 0? Just try
Zero.
acting on 0 over here. 0 is A, and you get 0. Now you define A to B, A dash of A 0, and leave it to you as an exercise to show that the energy of K defined this way is just omega K. So this omega K is nothing but square root of K squared plus K vector squared plus M squared. So we interpret this K as a single particle state. So if you think about it, we have fields and particles are emergent out of the field. These A daggers are fields, right? It's part of the decomposition of the fields. Now, if you have a vacuum, that means the ground state of the Hamiltonian, which you can think of as nothing, and A dagger sort of creates a one particle state. That's a very misleading statement to say, because if you can create something, wouldn't that violate energy conservation? So this is just a way of representing things. Shouldn't take this literally. With that I end. I completed canonical quantization completely. Next week we will discuss energy reduction, which I promise I will not go as fast as today.
That was the best. That was the best.